Our next speaker is Professor Sonia Chernova. Sonia is an associate professor in the School of Interactive Computing at Georgia Tech. She received her PhD from SAMU and was a postdoctoral associate at the MIT Media Lab. I've learned a lot about Sonia's research from many of her papers on interactive reinforcement learning and learning from demonstrations, which is another super exciting and important aspect to bring together perception and control. So her work also covers semantic reasoning, adjustable autonomy, human computation, and cloud robotics. I hope we'll learn more about these topics from Sonia in her talk and the panel discussion today. Let's welcome Sonia.
Thanks so much for the introduction. Can you see my slides?
Yes.
Yes. Okay. All right. Thank you. Just making sure. Thanks so much for having me. I'm really excited to be at this workshop. As Quan said, I'm a faculty member at Georgia Tech. I'm also currently on sabbatical at Facebook AI Research. And I want to talk about some of our recent work on semantic grasping. As was said in the intro, I do a wide range of work, maybe a little too wide sometimes. But I want to start by telling you a little bit about our path towards the work that I'll be presenting and talk about manipulation, some of our work on manipulation in general. So I'll start with a video highlighting the ICRA 2019 FetchIt Mobile Manipulation Challenge. This was really fun. This was in Montreal last year. Maybe some of you saw it in person. And this was a challenge to see, kind of evaluate the robustness of mobile manipulation techniques. And the robot had to operate autonomously for about 45 minutes, building these kits of various objects, doing some simulated kind of machining, using that shunk machine over the bottom. This is one of the workshop organizers. They're looking for photo opportunities. And our team was very fortunate to have won this challenge and beat out the other teams and had really great performance overall. And a lot of that work focused on kind of power grasping. So how do robots pick stuff up, figure out that it's picked something up robustly, place it in the right location. So, you know, really what made this work for us was, first of all, developing our entire software stack with a lot of kind of redundancy and error correction and very stable power grasp manipulation code. So that's written up in an ISRR paper if you ever want to take a look. But it also is a very hand-coded task, right? We know exactly which objects are there, and we really wrote this code for this task. It really has limited ability as the code itself, you know, the objects that we're retraining the robot to interact with, to scale. The framework itself scales to other, or generalizes to other domains, but the manipulation, you know, really we fine-tuned it for this application to make the challenge work. I'll also highlight another piece of work that was recently published in IGIR, and that looked at a very different problem of manipulation, and that's of remote teleoperation by a human user. And so the autonomy is a little bit more limited here, but in this work, we were looking at how do people teleoperate robots for not just pick and place, but object-specific manipulation task. How do you specifically make the robot grab a bottle for pouring, a drawer for opening, and so on. We worked with a robot manipulator, a JACO arm, which is at the bottom, in the bottom figure, but our funding comes from NASA, and actually we've done a lot of testing on their AstroBee platform and simulation, which is NASA's free-flying robot for the International Space Station. And it has a small gripper as well. And so kind of some interesting takeaways from that work, we found that reducing how much control a user has over the degrees of freedom of a grasp actually yields the best performance, which is counterintuitive to us roboticists, right? Roboticists want to have the maximum control over our system in many cases. And what we found statistically significantly with 90 people that we ran this with is that relying on some elements of autonomy in this context really helps, and actually 2D interfaces when you're only streaming 2D data to the operator versus 3D also helps. So a couple of unintuitive and kind of surprising results in this large-scale study that we conducted, which were really interesting. And this got us thinking a lot about semantic grasps and how do we eventually make this autonomous, right? And looking at task-oriented manipulation, right? So not just how do I grab this object, but how do I grab it for this task? And that's really what I want to talk about today. And so today, the focus of my talk is this idea of semantic grasping. I'll be highlighting a particular paper that was just published at ICAREER last month. It presents a framework that we call CAGE, Context-Aware Grasping Engine, and Wei Yu Liu is really the lead here, and Angel Daruna did a lot of the work as well. And I'll highlight that there's like code and database sets available online and things like that. But to motivate this work, so obviously there's a long history of grasping and manipulation work in robotics. A lot of it is focused on stable grasping because stable, until you can get stable grasps, there's not a lot you can do. But now that we can do really reliable, stable grasping on a wide range of objects, the question is, which of these stable grasps do we pick in the context of a given application, right? And what do I mean by context? Well, for humans, if we're picking up a pen and we're going to write with the pen versus hand a pen to somebody, we grasp it differently. And it's the same idea with a robot. How do we leverage the context of a task and how the object will be used in order to figure out which grasp to select? And that context can mean many things. It could be the material of the object. It could be its state. Is it clean, dirty, hot, cold? Is it full of liquid? Right? And what are you going to do with it? Are you going to use it to chop something? Are you going to hand it to somebody, et cetera? So all of these things, all of these pieces of information are important to figure out the right grasp. And this is a problem called semantic grasping. Now, we're not the first to explore this area. There's been prior work, growing amount of work in this exciting area. And I've kind of clustered in prior work into two general approaches. One is low-level features, so really relying, seeing kind of how you can train a system that relies on low-level visual features to figure out how to apply these semantic context across objects. So for example, prior work on using fast point feature histograms or FPFH around the selected grasp region to determine how an object should be grasped, or more specifically, whether a specific, unique grasp is valid or not in a given context. The challenge of using only low-level features for this work is that if you look at it, the visual aspects of each of these objects, even objects within the same category, like the bottles on the bottom, the visual features are very, very different, right? So generalizing, given only this data, is really, really hard. And so you really, I think, benefit from having some sort of higher level abstraction on top of this visual information. And there's been prior work on leveraging very high level abstraction. For example, there've been a number of kind of semantic rule-based approaches, such as, if let's encode the idea that if an object is a spatula and you're going to be lifting something, maybe you should grasp the handle. So there's been some prior work on generating such rules, often manually. And the problem with that, one of the core limitations of that kind of approach is if you have a lot of objects, this becomes intractable. It's not just a lot of objects, right? It's a lot of contexts. This object used in such and such a way when it was clean or dirty, and full or empty, and so on. And so the more information you have, the combinatorially everything explodes, and it gets harder and harder to encode such rules. And so what we tried to do with the context-aware grasping engine is really try to go for as much generalization as possible while still being able to train a system from data. And so what we contributed in this work is a semantic representation that we think is novel. Well, it is novel, and it combines a wider scope of context than has previously been used. This includes affordances of the object, their material, the physical material of the object state, and the task it's being used for. And then we learn a model from data that it determines whether a grasp is suitable or not within the context of all that information. And the other thing we did is released a large-scale grasping data set, which we call SG 14,000. And really what it contains is the largest to date data set of semantic grasps. So it's 14,000 semantic grasps over 44 different objects, 7 tasks, and 6 object states. And this is wide openly available at this point. So without further ado, let me just jump in and tell you some of the details about the context we're using. We're looking at 3 sources of data. One is just data about the object that's kind of task relevant. And that happens to be what the task is. Are you scooping? Are you handing somebody something? Are you chopping? And the other is the object state. Is it empty, full, hot, cold, and so on? There's prior work on detecting these automatically from kind of plan information. In this case, that information we're assuming is given to us. So that's one way we're cheating, so to speak. We're assuming that those labels are available. We're not really cheating on anything else, though. We're using RGBD data, point cloud data to actually sense the object in front of the robot. And we're even detecting the material of the object directly from the object itself using a handheld spectroscopy sensor. So you'll see a video shortly about the robot using this. So, and there's a paper from ICRA 2019. It was one of the best paper nominees showing that you can use spectroscopy, handheld spectroscopy for material recognition. So we're leveraging that work here. All right, so a little bit more detail. As I said, the task information, like, hey, you're looking at a scoop, or you're looking to do a scooping action, is given to us. We know that this object state is empty, that the current spatula is empty. We're going to use RGBD data to identify this object. We're going to get an object label, so this is a spatula. And the other thing we're going to extract from it are the affordances of the various parts of the object. So we're actually using prior work by other authors to segment the object into functional parts and then obtain a label for the affordance of each of those parts. Now you can see those affordances are a little bit abstract, but they're still very helpful. So in this case, the affordances are that the handle is for grasping and that there's this other part, which is a support part. That's kind of the action part of it, but it's not quite sure what it does, okay? And so this is information that's fed into our model. One quick aside, this is not the only way you could semantically segment objects. And so just kind of really quickly want to highlight that our approach kind of tries to segment by affordances here at the top. Other works have proposed other ways of segmenting. So it's by functional aspect of the part, for example, right here on the bottom, we see like the top versus the support base of an object being differently segmented. We use this approach because we feel it, in our experience, it generalizes across objects better. So for example, grasping, knowing that you should grasp the spatula by the support part when you're handing it to somebody rather than by the grasp part is kind of a generalizable concept that you can apply to other objects. We also found that this type of segmentation, which we didn't develop, we're kind of leveraging prior work here, generalizes really well across various shapes, even between object classes here at the bottom. You can really understand that which part of the object really has the contain affordance. And that's really, really important to generalizing across objects when you're figuring out how to grasp them best for a given task. Okay. All right, so that's how we segment the object. Here is the material recognition part. I'll show you a video of the robot obtaining the material for this object. That's all it is. It uses the spectroscopy sensor. From that, it gets like a 300-dimensional vector of data, which we can use to classify what this object is made out of. And, you know, why is this information useful? Well, for example, you could say, you know what, the robot should learn that you shouldn't grab sharp knives if they're metal, but it's totally okay to grab a knife by the blade if the blade is plastic, because that's not going to injure the sensors on the robot's gripper or anything else, right? And there's other examples of this, you know, generalizing to other tasks. Maybe you shouldn't put metal things in the microwave, things like that. There's other reasons materials are important. Okay, and so the final piece here, let's finish the animation. The final piece of data that we have is that we take all this information and we associate it with grasps. And so given a 3D model, sorry, but there is no 3D model. Given an object we sense from RGBD, we use an off-the-shelf sampler to sample stable grasps. So we have a bunch of candidate grasps all over this object. And that's what's kind of visualized here. It's a little hard to see. And for each of them, we associate its context, a context with that grasp. So here, this red grasp, on this part of the label, you can see it's going through the support portion of the ladle. And so with that grasp, we associate the support context information, for example. All right, so this is what our state representation is, basically. And given all this information, the question is, how do we know whether a grasp is good or not? And so for this, we use something called the wide and deep model, which came out of Google AI a few years ago. They developed it for recommender systems. And what this model does basically is give an X, which is the descriptor here at the top, describing the context for a given grasp. The model gives you P of Y given X, right? The probability of how suitable that grasp is for that given context. You know, the benefit of this wide and deep model, in case you haven't seen it before, is it's basically a combination of two models. One is designed for memorization, and the other one's designed for generalization. And if you combine them both, you can get both memorization and generalization with the benefits sort of both, while mitigating the individual weaknesses to a degree of both models. So you get to memorize specific rules that are really, you know, maybe something specific about knives that you really want your system to know very explicitly. If there's examples of that, the wide part of the model will learn that, and the deep will help you generalize. And so a little bit more detail on that. And again, you can kind of go back to the original Google paper for details on the model itself, or look at our paper. We talk about how we train these models. But the wide component is a linear model with a wide set of cross-product feature transformations. And these capture how the co-occurrence of the various input features, so this context that we're putting in it, how the co-occurrence of those features correlates with the particular label, in our case, suitable or not suitable grasp, right? And an example of the type of thing that this would be good for is, you know, training the robot to avoid grasping the contained portion of an object when it's trying to pour, right? For part of a cup when it's trying to pour. And so it's very specific. It's like, okay, I shouldn't do that. Got it. The second component is this deep component. It has dense embedding vectors for the data that's being put in, all these features. And then it has multiple hidden layers to kind of process that. And this is really responsible for unifying the previously seen data and generalizing to new instances. So for example, if you're learning a pouring task, this is the part of the model that would say, well, for pouring tasks, we know not to cover the opening. And so maybe the same is true for scooping tasks, right? That when you're scooping, you also shouldn't cover the opening. And so this is part of the model where this kind of reasoning would come in. And together, you know, the idea is that this model learns to both generalize to new contexts, as well as what I'll show in the results, that we can generalize to objects that have never even been seen before. And that's really powerful, right? That you're really now applying semantic grasping to completely held out objects and looking at generalization to brand new items, okay? All right, and the output of this, as I said, is that just a score, right, for each grasp, how suitable it is. And when we go through various grasps, we score them, and then we just select the highest scored grasp. And here's our running example here has been this label or scoop, whatever. We're going to be scooping with it. And so the robots decided to grasp that ladle by the handle for scooping, which is the correct thing to do. Okay. So for our evaluation, we used this data set that I mentioned. On the bottom, probably the information you're most interested in would probably be the bottom part, where we have many, many cups, spatulas, bowls, pans, bottles that have different material properties. They have different tasks like pouring, scooping, poking, cutting, handing, and so on. And we have a set of states. And again, we label those by hand at this point, whether it's something that's full or empty, hot or cold, and so on. And we have a few baselines. Oh, I should mention one important thing about this data set. In total, across this data set, there are 700 contexts. And this is a big number, right? Where context is just really this permutation of object, material, task, state. And so this gives us a lot of diversity for testing generalization across this domain. Okay, and so the baselines, we're going to do context agnostic, CA. What all that means is, you know, stable grasps that don't care about semantics whatsoever. We're going to look at 2 prior works that leverage semantics, which is classification of visual features and frequency table of affordances. And then both of those use low-level kind of visual features. The FT one looks at basically learns a co-occurrence frequency between the things it's learned, objects it's been trained on. And one quick note that we're not using any baselines from kind of that group of techniques that rely on rule-based methods, again, because we have 700 contexts. Writing 700 rules by hand would be very time-consuming, so we didn't do that. And the metric we report is average precision for the ranked grasp. And so for all results that we report, we trained on 70% of the data, which in this case, 70% of the contexts, and we test on 30%. And what we see is that our method outperforms the others by statistically significant margins. And again, it's very effective at learning from data, but it's just also very effective at generalizing to things it hasn't seen before because of this wide and deep network. And to validate that, we actually did test 2 things. One is, do we need both the wide and deep component of the model? Are they both helping? And the answer is yes, if you do an ablation study and cut either wide or deep, things get worse. And then the other thing we did was cut some of the context. We tried cutting every bit of context and to see whether, is there anything in our context that's not being used by the model or is hurting maybe. And again, anytime we cut any of the context, we see performance drop. And so again, all of this information, material, what is it, you know, what is the state of the object, what's the task, all of that information is highly relevant here, and our model makes use of that information really well. A quick demo that nothing would be satisfactory here without an actual robot demo. So those were results on the data set. We also did some results on a physical robot. We had 32 withheld contexts that we never trained on. We placed objects in front of the robot and told it what that object was going to be used for and what its state was. And out of 32, it got all those contexts correct in terms of which grasps it should use. The robot actually failed one of the grasps just because it's a robot and grasps sometimes fail. But the classification was actually correct. And so here's a brief video of some of those highlights. I'll pause it in a second. So here, depending on what task you're using, right? So this is the same object in the same state. They're both empty. But depending if you're going to be scooping on the left or handing it to somebody on the right, the robot selects a different way to hold the object. Let's see what else. Here's an opposite example. In this case, in both cases, this is a cup, and we want to hand it to somebody. But on the left, the cup is hot. It's on the inside is hot, and on the right, it's empty. And hot implies that it's full and empty as far as the training data. In the training data, we say, don't grasp hot parts. So if you have like a frying pan, you don't grab the hot part. It'll melt things, right? And so here we again see that it knows that it should hand over typically the way it's shown on the right by handing you something with the handle pointing towards you. But it also learns that if the cup is hot, then it should go ahead and grab the handle anyway to avoid grabbing something hot. And then this is a generalization to a cup. It just has never seen this cup, but it has seen the class of cups. And this is generalization across object classes, which is a really interesting case. And we're one of the few, I think, papers to show this, is that it's never even seen this saucepan type thing on the right. And it's certainly never seen it in this context. We're asking it to poke or stab somebody with it. And it's having to generalize the fact that, you know, for other similar objects that it's seen on the left, this ladle, this is how you would grab by the contain part to go poke somebody with the long handle, and it's generalizing that to the right side, and similarly going to poke somebody with the handle. So there we go. Oops. We only need that once. All right. And so in summary, kind of my takeaway from this talk is I hope more people get excited about this idea of kind of semantic grasping and looking at the really rich world of grasping in the context of tasks, right? Task-oriented manipulation. And I think what our work shows is that you really do need to have very rich state representations, that robots will benefit from having a richer state representation in the context of such problems. And we show this wide and deep model does appear to work really well in such a context. There's likely, you know, I'm looking forward to other people coming up with even better models, but we had good results with this one so far. And we also released our data set. So if you want to find our code or our data set, it's available at that link. And I'm going to pause there for questions. Thank you.
Thank you, Sonia, for the great talk. Any questions from the audience? So, we got one from QA. A question from Carl. How do you learn how now to grasp hot parts? Is that specified as part of the training data? If so, do you have thoughts on how you could learn these constraints from data?
It's entirely learned from data. That's a great question. It's not a rule that we made, but it is the label that exists in other parts of the data set. So we've labeled basically whenever something is hot, like a saucepan, we label all the grasps associated with the hot part as not desirable in the training data. So the model does end up learning that.
We'll take just one more. So a question from Swami. How does it generalize for grasping soft materials?
Soft materials?
That's right. I guess it's like a deformable objects.
Deformable objects.
Kind of
okay, great. That's a really cool question. I have no idea because we haven't tested any deformable objects. I will say that the material classification does work on foam. We didn't actually, I don't think we have any foam objects in this particular data set. We've done it for others. But our grasp generation sampler assumes rigid objects at this point. We're actually using Rob Platt's code for the just sampling grasps on the object. And it definitely assumes rigid objects. I would love to see how this applies to soft objects as well.
Yeah, that would definitely be like very exciting topics. Let's thank Sonia again. Thank you.
Thanks.